So welcome back to Topcast. This is part 2 of a 2-part series. In the first part, which I strongly recommend you listen to before listening to this one, I discussed It from Bit, which is not the name of a paper, but rather the name of a doctrine developed by John Wheeler, which serves as inspiration for a whole bunch of different papers, one of which is this one here that I'm going to read by David Deutsch. That first part not only discusses that doctrine and the paper from which it comes, but also background to this paper and where it appears and why it was written at all. In particular, the importance and significance of John Wheeler as a physicist and as a person and as someone who contributed across many, many areas of physics, not least of which is general relativity, and where I concluded in the last part his very expertise in general relativity that exceeded possibly anyone's who's ever lived might have coloured the reason why he was seemingly insisting upon the fact that the space-time continuum was not fundamental, and in fact you needed to quantize space in a way, that it came down to binary digits of a sort. All right, so that's that. Now we are on to the meat of the matter. The long promised, if you listen to the last episode, It from Qubits by David Deutsch, published in September 2002 from this book. I'm reading from the PDF that is available on his website if you want to read along. And so let's just get into it. Introduction. David writes, quote, "Of John Wheeler's really big questions, the one on which most progress has been made is it from bit. Does information play a significant role at the foundations of physics? It is perhaps less ambitious than some of the other questions, such as how come existence? Because it does not necessarily require a metaphysical answer. And unlike, say, why the quantum, it does not require the discovery of new laws of nature. There was room for hope that it might be answered through a better understanding of the laws as we currently know them, particularly of quantum physics. And this is what has happened. The better understanding is the quantum theory of information and computation," end quote. So yes, this it from bit question, the question about whether or not the fundamental nature of physical reality consists of information or, let's say, particles or material stuff or space-time continuums, that kind of thing. At least that's answerable within the conception of physics as we understand it. We just have to come to a better understanding of what it is we already know, okay? That's a less ambitious project than trying to figure out why does existence exist or why is the world quantum full stop, okay, that kind of thing. That would need new physics in the second case, why the quantum, and now why is there any existence? Well, then you've got a metaphysical question on your hands. David goes on to say, quote, "How might our conception of the quantum physical world have been different if it from bit had been a motivation from the outset? No one knows how to derive it, the nature of the physical world, from bit, the idea that information plays a significant role at the foundations of physics. And I shall argue that this will never be possible. But we can do the next best thing. We can start from the qubit." Wonderful. And next section, David writes, titled Qubits, quote, "To a classical information theorist, a bit is an abstraction, a certain amount of information. To a programmer, a bit is a Boolean variable. To an engineer, a bit is a flip-flop, a piece of hardware that is stable in either of two physical states. And to a physicist, quantum information theory differs in many ways from its classical predecessor. One reason is that quantum theory provides a new answer to the ancient dispute dating back to the Stoics and Epicureans, and even earlier, about whether the world is discrete or continuous. Logic is discrete. It forbids any middle between true and false. Yet in classical physics, discrete information process is a derivative and rather awkward concept." Pausing there, my reflection. David says there, logic is discrete. It forbids any middle between true and false. But of course, David is irritatingly rational and reasonable, isn't he? If only he would embrace a more open-minded view of the law of the excluded middle. The law of the excluded middle is this idea that David is stating there. In logic, things are true or false. You're either in the room right now or you're not. Okay, I'm either here delivering this podcast to you now or I'm not. I'm not both doing that. Forget the multiverse. We're just talking about this universe. In this universe now, either you are watching me now or you're not. And the fact that you're hearing this means that you are. There's no middling. There's no part way in between true and false. Things are true or they are false. Full stop. End of story. Yes, there has been some attempt to try and make alternative logics, but those logics allow for contradictions, unreason, irrationality. In the literal sense of all of those words, things become illogical. The foundational, most important law of logic upon which you want to develop an understanding of the world needs to rest upon either the thing that you're saying has some truth to it, is true, or it is strictly speaking false in some way. Okay, so the possibility of ruling things out rests upon this notion that there is no middle between true and false. Okay, let's keep going. David writes, quote, "The fundamental classical observables vary continuously with time, and if they are fields, with space too, and they obey differential equations. When classical physicists spoke of discrete observable quantities, such as how many moons a planet had, they were referring to an idealization, for in reality there would have been a continuum of possible states of affairs between a particular moon's being in orbit around the planet and just passing by, each designated by a different real number or numbers. Any two such sets of real numbers, however close, would refer to physically different states which would evolve differently over time and have different physical effects. Indeed, the differences between them would typically grow exponentially with time because of the instability of classical dynamics known as chaos. Thus, since even one real variable is equivalent to an infinity of independent discrete variables, say the infinite sequence of zeros and ones in its binary expansion, an infinite amount of in-principle observable information will be present in any classical object." End quote, pausing there in my reflection. So a whole bunch of things to say there. Firstly, if the world was classical, then you could never specify things precisely. You would always need an infinite decimal expansion in order to represent the physical quantities, because different physical states would require this infinite precision. There would be at a place which you couldn't specify exactly. You would need an infinite amount of in-principle observable information there, encoded somehow in real space-time, if the world was classical. And this also leads to the idea of chaos, discussed in The Fabric of Reality, Chapter 9, Quantum Computers, and in my episodes on those chapters there. This chaos or butterfly effect about the fact that ever so slight differences in classical systems between the initial conditions are going to amplify over time to cause radically different outcomes as time goes on, which just become amplified. The differences between them would typically grow exponentially with time, as David says right there. But reality is not classical. Reality is quantum, and so there is a finite amount of information in any bit of space-time, and it is determined by Planck's constant, among other things, that you have these discrete steps between one physical observable and another. Yeah, it's not a continuum between them, there's discrete amounts. Okay, so let's go on to the next section. David mentions here in this next section, to kind of steal some of his thunder, Zeno's paradox. So it's going to introduce the idea about how it is that we get from one particular place to another in a world that is governed by the discrete, in one sense. As far as quantum theory is concerned, we can't say that the world is discrete or that the world is continuous. It's both. Now, how can that be possible? Well, because you always only ever find yourself in a particular universe where you're observing, the electron orbiting the nucleus at one energy level. Or you're finding yourself in a universe where you find the electron orbiting at a different energy level, but never the intermediate state. And so this raises the question of how it is that in universes where electrons only have the possibility of being in one of those two states, how it gets from the lower state, let's say, to the higher energy state. Well, because in the multiverse, the proportion of universes where the electron is in, let's say, the ground state, the lowest possible energy state, has a certain proportion, but will change continuously Okay, so the multiverse, the proportion of universes, changes continuously until all of the universes are universes where the electron has the higher energy level, has the higher energy state. And that's how the transition occurs. Even though for any one universe, it's in one or the other state, discrete, the multiverse itself has this capacity to continuously change. And so this is how we reconcile the continuous and the discrete in our present best understanding of physical reality. This too is explained in chapter 9 of The Fabric of Reality. But let's go to what David says here, talking about the continuum, real numbers, non-discrete stuff. David says, quote, "Despite this ontological extravagance, the continuum is a very natural idea. But then, so is the idea, which is the essence of information processing, and therefore of it from bit, that complicated processes can be analysed as combinations of simple ones. These two ideas have not been easy to reconcile. With the benefit of hindsight, I think that this is what Zeno's paradox of the impossibility of motion was really about. Had he been familiar with classical physics and the concept of information process, he might have put it something like this. Consider the flight of an arrow as described in classical physics. To understand what happens during the flight, we could try to regard the real valued position coordinates of the arrow as pieces of information, and the flight as a computation process that processes that information. And we could try to analyse that computation as a sequence of elementary computations. But in that case, what is the elementary operation in question? If we regard the flight as consisting of a finite number of shorter flights, then each of them is, by any straightforward measure, exactly as complicated as the whole. It comprises exactly as many sub-steps, and the positions that the arrow takes during it are in one-to-one correspondence with those of the whole flight. Yet if, alternatively, we regard the flight as consisting of a literally infinite number of infinitesimal steps, what exactly is the effect of such a step? Since there is no such thing as a real number infinitesimally greater than another, we cannot characterize the effect of this infinitesimal operation as the transformation of one real number into another. And so we cannot characterize it as an elementary computation performed on what we are trying to regard as information. Pausing there, my reflection. Yes, so that's the computational way of putting this classic Zeno's paradox. And two ways there. One is to say that, well, the arrow is moving an infinitesimal amount each time, but if it's moving an infinitesimal amount each time, then there's an infinite number of such infinitesimal amounts for it to move. So if I want to, reach out and touch the microphone here, I have to go half the distance again, half the distance again, half the distance again, and I never actually get there because each of those half distances requires some finite amount of time. It would be an infinite amount of small but finite amounts of time. That's an infinite amount of time. On the other hand, you could regard that the distance between here and there, here in the microphone, is made up of a finite number of smaller numbers of intervals, but each of those finite intervals is themselves made of what? More finite intervals on ad infinitum, so we've still got a problem there. Okay. The resolution is that we're confusing the abstract mathematics of the situation with what goes on in physical reality. That's the resolution. Confusing what is an infinite number of points in abstract space and how to add those up with what can actually occur in physics. And what occurs in physics, of course, I can touch anything that I like. I'm not bound by Zeno's paradox. Zeno's paradox is a problem for pure mathematics. And even then, you have the capacity that's called a limit, right? The capacity to add up an infinite number of things and get a finite number. So that's one way of dealing with it. And the way in physics to deal with that, so that's one answer, one solution to it. And the other is that, well, physics simply allows you to traverse space in a finite amount of time. So that just is what's going on. And so therefore we have to accept that the laws of physics permit that to occur. And they do permit it to occur. Anyone who says that's not permitted because of Zeno's paradox is refuted immediately by experiment, observation, by showing them that you can do such a thing. David goes on to say, quote, "For this sort of reason, it from bit would be a non-starter in classical physics. It is noteworthy that the black body problem which drove Max Planck unwillingly to formulate the first quantum theory was also a consequence of the infinite information carrying capacity of the classical continuum. In quantum theory, it is continuous observables that do not fit naturally into the formalism, hence the name quantum theory. And that raises another paradox, in a sense the converse of Zeno's. If the spectrum of an observable quantity, the set of possible outcomes of measuring it, is not a continuous range but a discrete set of values, how does the system ever make the transition from one of those values to another? The remarkable answer given by quantum theory is that it makes it continuously. It can do that because a quantum observable, the basic descriptor of quantum reality, is neither a real variable, like a classical degree of freedom, nor a discrete variable, like a classical bit, but a more complicated object that has both continuous and discrete aspects. Pausing there, my reflection. This is my interpretation. Could be wrong. My interpretation is this is what a qubit is, right? A qubit can take on the 0 or the 1. There's your discrete. But also it can transition continuously between them. And, using the block sphere, it can take on the values in between those things. But we have those discrete values and the continuum of transitions between them. Now we begin to get a little technical, by the way. So I'll read this. I'll put this up on the screen and we'll read this paragraph together. When investigating the foundations of quantum theory, and especially the role of information, it is best to use the Heisenberg picture, in which quantum observables, which I shall mark with a caret as in x hat t, change with time, and the quantum state of psi is constant. Though the Schrödinger picture is equivalent for all predictive purposes, and more efficient for most calculations, it is very bad at representing information flow and has given rise to widespread misconceptions. See Deutsch and Herein. End quote. Pausing there. Okay, I'm not going to linger over Deutsch and Herein now. That could take some distant future episode of Topcast to consider. Observables, not represented as single numbers. The thing about this Schrödinger picture, two ways of looking at quantum theory. The Schrödinger picture, which is the wave function idea, and the Heisenberg picture, where observables are not represented as single numbers, they're represented as matrices, or better yet, the matrices are themselves the numbers being represented by matrices, okay, the observables represented as matrices. It's all rather technical and approaching the very limits of my pay grade, so to speak. So I can't go into that right now. Let's continue. David writes, quote, apart from the trivial observables that are multiples of the unit observable 1 hat, and hence only have one eigenvalue, the simplest type of quantum observable is a Boolean observable, defined as one with exactly two eigenvalues. This is the closest thing that quantum physics has to the programmer's idea of a Boolean variable. But the engineer's flip-flop is not just an observable. It is a whole physical system. The simplest quantum system that contains a Boolean observable is a qubit. Equivalently, a qubit can be defined as any system, all of whose non-trivial observables are Boolean. Just pausing there, my reflection. What I want to emphasize here, because it's going to come into the conclusion, and it's important to keep in mind right now, the observables, the engineer's flip-flop, the binary digit, whatever, Boolean variable, is a whole physical system. The simplest quantum system that contains a Boolean observable is a qubit. Qubits are physical things. They're physical things. It's important to keep that in mind. Okay, the Boolean variable rather, is a whole physical system. The simplest quantum system that contains such a Boolean observable, okay, a true-false, a 1-0, is a qubit, the physical system. Let's keep going. David says, quote, qubits are also known as quantum two-state systems. Although this is rather misleading because, like all quantum systems, a qubit has a continuum of physical states available to it. The spin of a spin-half particle, such as an electron, is an example. The fact that a qubit is a type of physical system, rather than a pure abstraction, is another important conceptual difference between the classical and quantum theories of information. Let me repeat that. And you might wonder why I'm emphasizing this, but it will become glaringly obvious towards the end, if you cannot already foresee why. The fact that a qubit is a type of physical system rather than a pure abstraction is another important conceptual difference between the classical and quantum theories of information. End quote. If you think the world is all information, these ideas that have reared up over the years, over the decades, over the centuries, millennia perhaps, some form of idealism, where you have information as the base reality. What David's saying here is the most fundamental theory of information is the quantum theory of information, the base unit of which is the qubit, the nature of which is physical. It's a physical thing. It's not purely in the abstract. It's not out there in Platonic ideal reality. It's here in physical reality. Important to know. Now, I'm skipping the next few paragraphs, couple of paragraphs, because they are technical. Picking it up where David writes, quote, "The classical information storage capacity of a qubit is exactly 1 bit, but there is no elementary entity in nature corresponding to a bit. It is qubits that occur in nature. Bits, Boolean variables, and classical computation are all emergent or approximate properties of qubits, manifested mainly when they undergo decoherence." Just pausing there, my reflection. Brilliant. Again, just to re-emphasize, qubits are physical things. They're not abstract ideals. They're physical things. Skipping a little, David goes on to say, quote, "In physical implementations, qubits are always subsystems of other quantum systems, such as photons or electrons, which are themselves manipulated via a larger apparatus in order to give the quantum computational network its defining properties. However, one of those properties is that the network is causally autonomous. That is to say, the law of motion of each qubit depends only on its own observables and those of other qubits of the network. And the motion of the external apparatus is independent of that of the qubits. Hence, all the external paraphernalia can be abstracted away when we study the properties of quantum computational networks." So just my reflection on that. In physical implementations, qubits are always photons, electrons, or something else. Okay, they're made of physical things. A qubit isn't just, let's think of it in the abstract, it's out there in the Platonic realm. I know I'm emphasizing this for like the 4th time now, but they have to be made of something. And in real life, experimental, nascent quantum computers, as people are trying to build right now, they're ions or they're photons or they're electrons. They're some sort of matter, some sort of material. Important to keep in mind, okay, for the philosophy of this, for the metaphysics of this, if you like, that's important to understand, to appreciate, okay? To the modern instantiation of this is Donald Hoffman, all right? People who want to have these grand ultimate theories of reality that say that stuff comes down to information, but ignore this, ignore our deepest theory of reality. Our deepest theory of reality is quantum computation, for the reasons I said earlier. Okay, we've got this unification of computation and quantum theory. So this is the deepest. Qubits are the fundamental nature of reality, but they're physical, and they need to be represented using some bit of matter or other, or particle anyway, photon. Now I'm skipping, again, quite a bit here, and I'm picking it up where David says, quote, "It might seem that the study of quantum computational networks is a narrow subspecies of physics. Qubits are special physical systems and are often realized as subsystems of what are normally considered elementary systems, such as elementary particles. In quantum gates, qubits interact in a rather unusual way. They strongly affect each other while remaining isolated from the environment. Their periods of interaction are synchronized, alternating with periods of inertness and so on. We even assume that all the qubits of the network start out with their spins pointing in, let's say, the plus z direction, or whatever the initial condition means for qubits that are not spin minus a half systems. None of these attributes is common in nature, and none can ever be realized perfectly in the laboratory. At the present state of technology, realizing them well enough to perform any useful computation is still a tremendously challenging, unattained target. Yet, quantum computational networks have another property which makes them far more worthy of both scientific and philosophical study than this way of describing them might suggest. The property is computational universality. Universality has several interrelated aspects, including the fact that a single standard type of quantum gate suffices to build quantum computational networks with arbitrary functionality. The fact that quantum computational networks are a universal model for computation. The fact that a universal quantum computer can simulate with arbitrary accuracy the behavior of arbitrary physical systems. The fact, not yet verified, that such computers can be constructed in practice. End quote. David has mentioned a couple of times now this concept of gates, quantum gates, or logic gates more broadly speaking. These are the physical things that allow for computation to occur in electronics. Traditionally in electronics you have AND gates, you have OR gates, you have NOT gates. These are logical operations. The universal gate is the NOT AND gate. Or there's a few universal ways of putting together gates such that you don't need any other gates. But the NOT AND gate, not AND, that can be used to do anything that you like, classically speaking. It's a universal gate. And so David's going to talk about universal gates, in fact, in the very next line. So he goes on to say, quote, "The first of those concerns universal gates. One of the ways in which the theory of quantum computation lives up to the it from bit intuition is that in the most natural sense, the computation performed by the component gates of a network can indeed be simpler than that performed by the network as a whole. The possible motions of 1 or 2 qubits through a gate, though continuous, are not isomorphic to the possible motions of a larger network, but by composing multiple instances of only a single type of gate that performs a fixed elementary operation, it is possible to construct networks performing arbitrary quantum computations. Any gate with this property is known as a universal quantum gate. It turns out that not only do there exist universal gates operating on only 2 qubits, but in the manifold of all possible 2-qubit gates, only a set of measure 0 are not universal. Thus, computational universality is a generic property of the simplest type of gate, which itself involves interactions between just 2 instances of the simplest type of quantum system. There are also other ways of expressing gate universality. For instance, the set of all single qubit gates, together with the controlled NOT operation, measurement of 1 qubit by another, also suffice to perform arbitrary computations. Alternatively, so do single qubit gates, together with the uniquely quantum operation of teleportation. All this constitutes a strikingly close connection between quantum computation and quantum physics, of which there were only hints in classical computation and classical physics. Models of classical computation based on idealized classical systems, such as billiard balls, have been constructed in theory, but they are unrealistic in several ways and unstable because of chaos, and no approximation to such a model could ever be a practical computer. Constructing a universal classical computer, such as Babbage's analytical engine, from elementary components that are well described in a classical approximation, such as cogs and levers, requires those components to be highly composite, precision-engineered objects, which would fail in their function if they had an even slightly different shape. The same is true of the individual transistors on the microchips that are used to build today's computers, classical computers. But it is not true, for instance, of the ions in an ion trap, one of the many quantum systems that are currently being investigated for possible use as quantum computers. In an ion trap, a group of ions is held in place in a straight line by an ingeniously shaped oscillating electric field. In each ion, one electron forms a 2-state system, the states being its ground state and one of its excited states, which constitutes a qubit. The ions interact with each other via a combination of the Coulomb force and an external electromagnetic field in the form of laser light, which is capable of causing the observables of any pair of the qubits to change continuously when the laser is on. The engineering problem ends there. Once an arrangement of that general description is realized, the specific form of the interaction does not matter. Because of the generic universality of quantum gates, there is bound to exist some sequence of laser pulses, each pulse constituting a gate affecting 2 of the qubits that will cause an n-ion trap to perform any desired n-qubit quantum computation. Pausing there, my reflection. Yes, so if you have these ions, the more you have, the more qubits you have. You can have 2. The University of New South Wales uses precisely this technique. Then there's no limit to the size of the quantum computer you can have. You just keep on having more ions participate in this kind of computation. Problem is, the more ions you have, the more likely the thing is to decohere, to allow the information that is in the quantum computer to leak to the outside world, and then you lose the capacity to compute. They can certainly do the 2-qubit case. Okay, that's been demonstrated. Maybe they're up to 4 now or something like that, but yeah, it uses very low temperatures. Go to my multiverse series on that. They need to use not merely liquid helium, but isotopes of helium in order to evaporative cool the whole system to stop it from decohering, vibrating. It's an engineering nightmare so far. But, progress is happening. David goes on to say, quote, "The same sort of thing applies in all the other physical systems. Nuclear spins, superconducting loops, trapped electrons, and many more exotic possibilities that serve or might one day serve as the elementary components of quantum computers. Lloyd, 1995, has summed this up in the aphorism, quote, "Almost any physical system becomes a quantum computer if you shine the right sort of light on it," end quote. There is no classical analogue of this aphorism. Quantum computers are far harder to engineer than classical computers, of course, but not for the same reason. Indeed, the problem is almost the opposite. It is not to engineer precisely defined composite systems for use as components, but rather to isolate the physically simplest systems that already exist in nature from the complex systems in their environment. That done, we have to find a way of allowing arbitrary pairs of them to interact in some way with each other. But once that is achieved in a given type of physical system, no shaping or machining is necessary because the interactions that quantum systems undergo, as a matter of course, are already computationally universal. The second aspect of universality is that quantum networks are a universal model for quantum computation. That is to say, consider any technology that could one day be used to perform computations, whether quantum or classical, and whether based on gates or anything else. For any computer C built using that technology, there exists a quantum computational network composed entirely of simple gates, such as instances of a single 2-qubit universal gate that has at least the same repertoire of computations as C. Here we mean the same repertoire in quite a strong sense, namely, given a computational task, say factorization, and an input, say an integer, the network could produce the same output as C does, say the factors of the integer, end quote. Now I'm skipping a few paragraphs here that are technical and picking it up where David says, quote, "The upshot is that the abstract study of quantum computations, as distinct from the study of how to implement them technologically, is effectively the same as the study of one particular class of quantum computational networks, which need only contain one type of universal quantum gate. This universality is the quantum generalization of that which exists in classical computation, where the study of all computations is effectively the same as the study of any one universal model, such as logic networks built of NAND gates or Toffoli gates, or the universal Turing machine. However, quantum universality has a further aspect which was only guessed at and turned out to be lacking. In the case of classical computation, quantum computational networks can simulate with arbitrary accuracy the behavior of arbitrary physical systems, and they can do so using resources that are at most polynomial in the complexity of the system being simulated. The most general way of describing quantum systems, of which we are at all confident, is as quantum fields," end quote. And once more, I'm skipping a sizable amount more, picking it up, where David says, quote, "In most practical computations, we should only be interested in the output for a given input and not, unless we are the programmer, in how it was brought about. But there are exceptions. An amusing example is given in the science fiction novel Permutation City by Greg Egan. In it, technology has reached the point where the computational states of human brains can be uploaded into a computer, and simulations of those brains, starting from those states, interact there with each other, and with a virtual reality environment, a self-contained world of the client's choice. Because these computations are expensive, the people who run the service are continually seeking ways to optimize the program that performs this simulation. They run an optimization algorithm which systematically examines the program, replacing pieces of code or data with other pieces that achieve the identical effect in fewer steps. The simulated people cannot, of course, perceive the effect of such optimizations, and yet eventually the optimization program halts, having deleted the entire simulation with all its data, and reports, "This program generates no output." By the way, there is no reason to believe that a universal quantum computer would be required for such simulations. See Tegmark 2000. There is every reason to believe that the brain is a universal classical computer. Nevertheless, this strong form of universality of quantum computation assures us that such a technology, and artificial intelligence in general, must be possible and tractable, regardless of how the brain works, provided, that is, that universal quantum computers can be built in practice. This is yet another aspect of universality, perhaps the most significant for the "it from qubits" question. Indeed, universality itself may not be considered quite as significant by many physicists and philosophers if it turns out that qubits cannot, in reality, be composed into networks with universal simulating capabilities. Okay, now, I'm just pausing because we're reaching the end here, and we're reaching the pinnacle, the conclusion, the main point of the physical and what I might say ontological or metaphysical consequences of this view of quantum computation being the fundamental theory of physical reality and the qubit being the fundamental unit of that theory of physical information. What David says here, he goes on to say, and this section is titled, quote, "The world is not made of information." Okay, he goes on to say, quote, "Let us suppose that universality does hold in all four of the above senses. Then since every physical system can be fully described as a collection of qubits, it is natural to wonder whether this can be taken further. Might it have been possible to start with such qubit fields and to interpret traditional quantum fields as emergent properties of them? The fact that all quantum systems that are known to occur in nature obey equations that look fairly simple in terms of the language of fields on spacetime is perhaps evidence against such naive qubits are fundamental view of reality." Pausing now my reflection. Why would that be evident if you have the idea that all quantum systems that occur in nature, obey equations that are fields on spacetime? Why would that mean qubits are not fundamental, or that it's evidence against the qubits are fundamental view of reality? Well, because that would mean that the fields and spacetime are fundamental. They're deeper, they're more important than the qubits, right? That's why you would avoid qubits are fundamental as being a conclusion if they are just, in the language of fields on spacetime. All right, push on. David says, quote, "On the other hand, we have some evidence in its favour too. One of the few things that we think we know about the quantum theory of gravity is expressed in the so-called Bekenstein bound. The entropy of any region of space cannot exceed a fixed constant times the surface area of the region." Bekenstein, 1981. "This strongly suggests that the complete state space of any spatially finite quantum system is finite, so that, in fact, it would contain only a finite number of independent qubits. But even if this most optimistic quantum computation-centered view of physics turned out to be true, it would not support the most ambitious ideas that have been suggested about the role that information might play at the foundation of physics. The most straightforward such idea, and also the most extreme, is that the whole of what we usually think of as reality is merely a program running on a gigantic computer, a great simulator. On the face of it, this might seem a promising approach to explaining the connections between physics and computation. Perhaps the reason why the laws of physics are expressible in terms of computer programs is that they are, in fact, computer programs. Perhaps the existence of computers in nature is a special case of the ability of computers, in this case the great simulator, to emulate other computers. The locality of the laws of physics is natural because complex computations are composed of elementary computations. Perhaps the great simulator is a quantum cellular automaton, and so on. But in fact, this whole line of speculation is a chimera. End quote, pausing there. Yes, if the entire universe is some great simulator, then you want to ask that if it's giving rise to what we perceive as the laws of physics, where is this simulator, and what laws of physics does it obey? Because it's clearly in a larger reality. It sits in that larger reality and it gives rise to our reality, what we perceive as reality. But there's something beyond our reality in which the great simulator finds itself, obeying different physical laws. It doesn't help if you're interested in deep explanations of the world. Let's get going. David says, quote, "It entails," in other words, the great simulator idea, "it entails giving up on explanation in science. It is in the very nature of computational universality that if we and our world were composed of software, we should have no means of understanding the real physics, the physics underlying the hardware of the great simulator itself. Of course, no one can prove that we are not software. Like all conspiracy theories, this one is untestable. But if we are to adopt the methodology of believing such theories, we may as well save ourselves the trouble of all that algebra and all those experiments and go back to explaining the world in terms of the sex lives of Greek gods. An apparently very different way of putting computation at the heart of physics is to postulate that all possible laws of physics, in some sense, are realized in nature, and then to try to explain the ones we see entirely as a selection effect. For example, Lee Small in 1997. But selection effects, by their very nature, can never be the whole explanation for the apparent regularities in the world. That is because making predictions about an ensemble of worlds, say with different laws of physics or different initial conditions, depends on the existence of a measure on the ensemble, making it meaningful to say things like, admittedly, most of them do not have property X, but most of the ones in which anyone exists to ask the question do. But there can be no a priori measure over all possible laws. Tegmark, 1997, and others have proposed that the complexity of the law, when it is expressed as a computer program, might be this elusive measure. But that merely raises the question, complexity according to which theory of computation? Classical and quantum computation, for instance, have very different complexity theories. Indeed, the very notion of complexity is irretrievably rooted in physics. So in this sense, physics is necessarily prior to any concept of computation. It cannot possibly come from bit or from qubit by this route. See also my criticism of Wheeler's law without law idea, Deutsch 1986, pausing there my reflection. Yes, but not right now. Okay, we will persevere through to just the last bit here. David goes on to say, both these approaches fail because they attempt to reverse the direction of the explanations that the real connections between physics and computation provide. They seem plausible only because they rely on a common misconception about the status of computation within mathematics. The misconception is that the set of computable functions, or the set of quantum computational tasks, has some a priori privileged status within mathematics, but it does not. The only thing that privileges that set of operations is that it is instantiated in the computationally universal laws of physics. It is only through our knowledge of physics that we know of the distinction between computable and non-computable, or between simple and complex. And the next section is titled, The World is Made of Qubits. And David says, quote, so what does that leave us with? Not something for nothing. Information does not create the world ex nihilo, nor a world whose laws are really just fiction, so that physics is just a form of literary criticism, but a world in which the stuff we call information and the processes we call computations really do have a special status. The world contains, or at least is ready to contain, universal computers. This idea is illuminating in a way that its mirror image, that a universal computer contains the world, never could be. The world is made of qubits. Every answer to a question about whether something that could be observed in nature is so or not is in reality a Boolean observable. Each Boolean observable is part of an entity, the qubit, that is fundamental to physical reality but very alien to our everyday experience. It is the simplest possible quantum system, and yet, like all quantum systems, it is literally not of this universe, part of the multiverse. If we prepare it carefully, so that one of its Boolean observables is sharp, it has the same value in all the universes in which we prepare it. Then according to the uncertainty principle, its other Boolean observables cease to be sharp. There is no way we can make the qubit as a whole, homogeneous across universes. Qubits are unequivocally multiversal objects. This is how they are able to undergo continuous changes, even though the outcome of measuring or being them is only ever one of a discrete set of possibilities. What we perceive to some degree of approximation as a world of single-valued variables is actually part of a larger reality in which the full answer to a yes-no question is never just yes or no, nor even both yes and no in parallel, but a quantum observable. Something that can be represented as a large Hermitian matrix. Is it really possible to conceive of the world, including ourselves, as being made of matrices in this sense? Zeno was in effect asking the same question about real numbers in classical physics. How can we be made of real numbers? To answer that question, we have to do as Zeno did and analyse the flow of information, the information processing that would occur if this conception of reality were true. Whether we could be made of matrices comes down to this. What sort of experiences would an observer composed entirely of matrices, living in a world of matrices, have? The theories of decoherence and consistent histories have answered this question in some detail. At a coarse-grained level, the world looks as though classical physics is true, and as though the classical theories of information and computation were true too. But where coherent quantum processes are underway, particularly quantum computations, there is no such appearance, and an exponentially richer structure comes into play. As Karl Popper noted, the outcome of solving a problem is never just a new theory, but always a new problem as well. In fundamental science, this means, paradoxically, that new discoveries are always disappointing for those who hope for a final answer. But it also means that they are doubly exhilarating for those who seek ever more and ever deeper knowledge. The argument that I used above to rule out great simulator type explanations has implications for genuine physics too. Although in one sense the quantum theory of computation contains the whole of physics, with the possible exception of quantum gravity, the very power of the principle of the universality of computation inherently limits the theory's scope. Universality means that computations and the laws of computation are independent of the underlying hardware, and therefore the quantum theory of computation cannot explain hardware. It cannot by itself explain why some things are technologically possible and others are not. For example, steam engines are, perpetual motion machines are not, and yet the quantum theory of computation knows nothing of the second law of thermodynamics. If a physical process can be simulated by a universal quantum computer, then so can its time reverse. An example closer to home is that of quantum computers themselves, the last aspect of universality that I mentioned above, that universal quantum computers can be built in practice, has not yet been verified. Indeed, there are physicists who doubt that it is true. At the present state of physics, this controversy, which is a very fundamental one from the it from qubit point of view, cannot be addressed from first principles. But if there is any truth in the it from qubit conception of physics that I have sketched here, then the quantum theory of computation as we know it must be a special case of a wider theory. Quantum constructor theory, Deutsch 2002, is the theory that predicts which objects can or cannot be constructed, and using what resources. It is currently in its infancy. We have only fragmentary knowledge of this type, such as the laws of thermodynamics, which can be interpreted as saying that certain types of machine, perpetual motion machines of the first and second kind, cannot be constructed, while others, heat engines with efficiencies approaching that of the Carnot cycle arbitrarily closely, can. One day, quantum constructor theory will likewise embody principles of nature which express the fact that certain types of information processing, say the computation of non-Turing computable functions of integers, cannot be realized in any technology, while others, the construction of universal quantum computers with arbitrary accuracy, can. Just as the quantum theory of computation is now the theory of computation, the previous theory developed by Turing and others being merely a limiting case, so the present theory of computation will one day be understood as a special case of quantum constructor theory, valid in the limit where we ignore all issues of hardware practicality. As Einstein in 1920 said, quote, "There could be no fairer destiny for any physical theory than that it should point the way to a more comprehensive theory in which it lives on as a limiting case," end quote. And end of the paper there, the chapter of the book about science and ultimate reality, there by David Deutsch, this paper, It from Qubit. So, what we know now is that the most fundamental theory of reality is quantum computation. And the basic unit is the qubit, of which any number of particles, ions perhaps, but also things more fundamental, like photons and electrons, can serve as instances of those qubits. Reality is that, base reality, if you like, as far as we know it. The observables of these fundamental particles, and you can call those qubits. And here's the kicker, as I emphasized throughout my discussion of this. Qubits are physical. Qubits are physical. If reality, as deeply as we know it, is information in some sense, but the basic unit of information is the qubit, and qubits are physical, then reality as we know it is physical. Basic fundamental reality is physical. Idealists everywhere who want base reality to be information or argue that it is information or ideas have to accept those things reduce to the most basic building blocks of information or ideas. Qubits. And qubits are physical. That's what we know reality consists of fundamentally, as far as we understand fundamental reality now. But as David says towards the end there, our search is not over. It never is. Because this is simply a limiting case of whatever the next theory is. Perhaps constructor theory, quantum constructor theory. That will be deeper, and that will tell us more than anything about what these theories, general relativity, quantum theory, quantum computation, have been able to so far. So that's a critique of Wheeler to some extent, but more importantly, it is what we know about physical reality right now. And the fact that this search for ever deeper understandings of reality never ends. Until next time, bye-bye.